So we're talking about, clean code, and you've mentioned specific code smells. What exactly are these smells?
Well, imagine a smelly room. You can picture it. Clean code is the opposite. These smells are coding patterns that create issues down the road.
Like what? Give me an example.
Duplicated code, for example. Copying and pasting code segments often leads to maintenance nightmares.
But sometimes copying and pasting is just faster, right?
Absolutely. There are times. But in the long run, a few extra lines of code will usually save tons of headaches.
So, these smells are essentially bad habits?
They're patterns of code that indicate a design problem.
Could you elaborate on refactoring? How does it relate to fixing these smells?
Refactoring is the process of restructuring existing code without changing its external behavior, essentially smelling the room for code smells and fixing the smell.
Sounds like a good analogy. Is this list of code smells exhaustive?
Not exhaustive, but a good starting point, a reference.
So, is it subjective? Does this depend on the coding language?
Some degree, sure. Different contexts, different needs.
So, there are exceptions or trade-offs,
Yeah. Temporary code or legacy code might have smells. Fixing them might not always be a priority.
Right. How can someone learn more about this? Are there particular resources that will help them?
Absolutely. Martin Fowler's book is a great starting point, and various online articles and tutorials can help you learn more.
It sounds like this is something you do all the time. What are your favorite techniques for refactoring?
Well, I tend to look for opportunities to extract methods for better modularity. Often it's about pulling out common code to reduce redundancy.
That sounds insightful. We've hit a good beat.
It's important to balance speed with long-term maintenance, right?
Absolutely. Thanks for the insights. Hey Robert, so we're talking about writing clean code, and it seems like part of that is having a really simple build process, right?
Absolutely, Andrew. A streamlined build and testing process is key to productivity and ultimately, clean code. Imagine spending hours figuring out the right sequence of commands just to build your project. It's like setting up a complicated maze, right?
Totally. It's frustrating. How can we make the build process, truly effortless?
Well, ideally, you want a single command to check out the code and another to build it. That removes a lot of the guesswork and memorization.
But what if it's a complex project? Wouldn't that approach stifle flexibility?
It's a valid concern, Andrew. There's a balance. For smaller projects and even many larger ones, streamlining is hugely beneficial. But for projects with very specific build requirements, you might need more complex scripts. Tools are key here.
You mean like using Make or Maven?
Exactly. Those tools can handle the intricate steps, allowing you to specify your needs through concise configuration files, making the process more flexible while remaining efficient.
So, we're looking for a trade-off between simplicity and the flexibility to handle complex situations?
Yeah, finding that sweet spot is important. It's not about eliminating all complexity, but rather organizing and automating it so it doesn't become a bottleneck.
Interesting. So, for most projects, is a single command for building and another for testing the gold standard?
It certainly is a good goal to strive for. But as you said, it's not always possible or even desirable.
Makes sense. Thanks, Robert.
You're welcome, Andrew.
Robert, we've been talking about crafting clean code. Today's focus, a multitude of specific rules. What's the biggest mistake developers make in terms of code structure?
Well, Andrew, duplication's a big one. Imagine copying code blocks over and over. It's messy, and it's hard to update. It's a clear sign of lacking abstraction.
Okay, so dry it is. How do we spot this duplication in code?
Sometimes it's blatant, whole blocks repeated. Other times it's subtle. A switch statement that does the same check over and over again is duplication needing refactoring.
Okay, so that's a switch statement refactored as polymorphism. Great. What about excessive coupling?
Yeah. Classes that depend heavily on other classes become brittle. It's the opposite of good abstraction.
What about dead code? How do we recognize it?
Dead code is like ghosts haunting the project. It's code that's never run. Clean up that code. It's a waste of memory.
So if there's dead code, just delete it?
Usually. But sometimes, dead code's a leftover from previous versions.
And the right level of abstraction?
Make your code flexible by separating high-level from low-level details.
So, we should keep those levels separate?
Exactly. It makes the code maintainable. Base classes shouldn't be too aware of their derivatives. That tightens up the code and promotes reuse.
Got it. What about feature envy?
A method that tries to do too much, by using another class's variables to perform an operation, that's feature envy.
Right, I see. So keep methods focused, you know?
Precisely.
So many rules, it's overwhelming. Where do we start?
Start with the most egregious issues. Duplication is often the worst offender, as it builds up like a bad habit.
What about excessive info in a class? What's the ideal way to tackle it?
Limit class methods and variables. Aim for small, focused interfaces.
Makes sense. Any advice for a junior dev just starting out?
Start with the fundamentals. Focus on dry, keep it modular, and embrace good abstractions. That's good habits.
So, we really want to avoid excessive coupling, then?
Yes, that is vital for maintenance and extension.
Thank you. Ugh, import statements. So many of them sometimes. It always feels like I'm wading through a swamp of import lines.
Chuckles, I hear ya. Sometimes those long import lists can be overwhelming, even distracting. A cleaner approach is often using wildcard imports.
Wildcard imports? How do those work?
Imagine you're using multiple components from a specific library. Instead of importing each one individually, you can use a wildcard import package to import all components from that package.
So you just import everything? That seems risky, right? What about name collisions?
Potentially. If two libraries have classes with the same name, but different packages, then you need to use fully qualified names, package.classname. It's a bit more typing but avoids conflicts. Modern IDEs usually handle this automatically. They can help convert wildcards to specific imports.
So, is this a definite best practice? It seems a trade-off between shorter imports and possible ambiguity.
Generally, yes. It's far more efficient. But if you have legacy code and you're dealing with the classes from within a specific package, knowing the exact imports is beneficial for identifying/analyzing relationships.
So, what about cases like a huge old code base? Wouldn't you need specific imports to understand dependencies there?
Absolutely. For that kind of analysis, specific imports would be helpful. You need to see what's actually there. But if you are using modern tools, it's just so easy to convert the imports once the project is updated to the new style.
That makes sense. Thanks for the clarity on that.
You're welcome. It's all about balancing readability with maintainability in a modern context.
Makes a lot of sense. So, is there anything you haven't addressed that I should be thinking about?
Generally, no. If you are working with legacy code, you need to know the specific imports to analyze the code properly. But most modern code is fairly maintainable with wildcard imports, unless there is a specific reason not to.
Great. That was really helpful. Robert, J2's critique of inheriting constants seems pretty strong. What are your thoughts on when and how static imports offer a better solution?
Yeah, inheriting constants from an interface is a code smell. It hides the origin of those constants deep in the inheritance hierarchy. Static imports bring them into the local scope, making it crystal clear where the values come from. Think of it like moving a commonly used tool from a toolbox to your workbench.
So, if you got a bunch of constants that are commonly used across several classes, are static imports the better choice every time?
Not necessarily. Sometimes, you might have a set of related constants that are more conceptually tied to a specific interface. If you have a set of constants that change frequently in different parts of your application, then static imports might not be the most ideal choice. There are cases for inheritance for constants.
Right. Enum seemed like a really neat feature, especially in this context of payroll. Can you elaborate on why they're a better choice than just using static constants?
Enums add a layer of type safety. You can't accidentally use a string or an integer where an enum is expected. Enums define an exhaustive set of possibilities. The compiler ensures you're using the correct value. Enums also come with inherent readability. Instead of just tense_br_week equals 400, you're saying payroll_constants tense_week, or rather, hourly pay grade journeyman rate.
That makes sense. Enums add another layer of safety to ensure you are only using specific values.
Precisely. Enums also let you add methods to those values. This is useful for adding additional logic tied directly to those constants, as you saw with the rate method in the hourly pay grade enum. Enums greatly enhance maintainability.
So, static imports help with readability and are useful in many cases.
Correct, but enums are a more powerful tool for adding type safety and semantic richness. If you're using them, you'll find your code is more expressive.
You mentioned potential downsides to enums. What might those be in a high-performance scenario?
There could be slight performance implications when using enums over simple constants, particularly in extremely performance-critical parts of an application. However, this is usually not a critical concern in most cases.
Thanks for clearing that up. This helps me understand the pros and cons of each approach.
Glad to help. Always aim for the clearest, most maintainable, and correct solution.
Hey Robert, great to have you on the show. We're diving deep into clean code today, and I'm really interested in this concept of naming. Is it just a matter of taste, or are there specific rules we should follow?
Well, Andrew, it's not just a matter of taste, although a good sense of style helps. Naming is actually critical to code readability. Imagine you're trying to follow directions written in complete gibberish. It's the same with code. Poorly chosen names make it a frustrating puzzle to solve.
So, you're saying names affect how easily we understand what the code is supposed to do?
Exactly. Look at this example. These cryptic variable and function names make the code a complete mystery. It hides the algorithm, the logic, and it's hard to anticipate what it does based on the code itself.
Okay, I see what you mean. Can you give me a few concrete examples of better names?
Absolutely. Instead of X and Q, a descriptive name like calculate score is much more illuminating. Variables like score and frame quickly communicate the intent of the calculation.
But wouldn't more descriptive names make the code longer?
Not necessarily. Sometimes it's about finding the right balance. A name like next two balls for strike is more complete but still concise and descriptive. The trade-off is worth it.
So how do you come up with these names? Any tips for finding the right wording?
It's about thinking about what the function or variable actually does. What is its purpose, and what would be the most clear way to describe it in short, understandable words? It often helps to step back and ask, what would I call this if I were explaining it to a colleague?
That makes sense. So what if you discover a flaw in the naming conventions down the line?
You're smart to point that out. Names, like software, evolve. Sometimes when reviewing code, you might discover that you need to update naming to better reflect the function's purpose or the module's overall design.
That makes it a dynamic process, constantly needing review and adaptation. Thanks for the insights, Robert.
Anytime, Andrew. It's all about making your code readable and maintainable over time.
So, Robert, you're saying choosing the right name is crucial for clean code?
Absolutely. Names reveal the essence of the code.
But how do we know when a name's too low level?
Look at the intent. Does the name reveal what the code does or how it's implemented?
The modem example shows a good illustration, right?
Yep, dial for a connection. It's implementation focused.
So, connect is a better option?
Precisely. It points to the behavior, connecting to something.
So it's about choosing names reflecting the concept, not the details?
Exactly. It's continuous code improvement.
This sounds time-consuming.
It's worth it.
How do we identify those low-level names?
By taking a critical look, revisiting code.
Is there any automation?
Some refactoring tools can help, but it's often a human judgment call.
But how do we find those names?
You must learn to think abstractly.
That sounds challenging.
Practice makes perfect.
So, we need to be constantly scrutinizing our names for more abstract concepts?
Yes, to improve code readability and maintainability.
Thanks for the insights.
You're welcome.
What if a method name is low-level but has a specific meaning in the context?
Look at the use case, then. If the method is only used in this specific context, a higher-level name might not apply.
Great point. Context matters.
Indeed.
So it's a trade-off between abstraction and maintaining context.
Correct. You want the best balance, tailored to your code.
So, Robert, we've talked about structure and algorithms. Now let's talk about making code understandable. How important is naming for readability?
Crucial. Clear names tell the story of your code. Bad names are like cryptic riddles.
So, Concrete examples?
Sure. Think Auto hang op modem decorator. It's self-explanatory. Whereas, modem decorator too. Not so much.
Okay, I see. But what about project-specific names? How do we balance those?
That's where ubiquitous language comes in. Teams often create a special vocabulary around their project, so everyone's on the same page.
Like a shared secret language?
Precisely. It makes the code's purpose instantly clear.
But what if a new guy joins?
Then we spend a bit of time onboarding them and clarifying the terms. Trade-offs for maintainability.
So, no universal standard, but consistent within each project?
Absolutely. Java's toString method is a standard.
Makes sense. Can you give an example of a project-specific convention?
In a project handling medical records, patient record processor or treatment plan manager makes sense.
So, it's not about being super creative, just consistent and relevant.
Exactly. Readability trumps creativity, in most cases.
Thanks for the insight. What about handling exceptions in a consistent way?
Very important, consistent naming and exception handling.
So naming helps you to easily remember the structure and the purpose of each piece of code, right?
Yep, makes reading and understanding code a lot easier.
Okay, now I understand. Thanks, Robert. Hey, Robert, we were talking about writing clean code, and it made me think naming things. How do you approach that?
It's a biggie, Andrew. Like, really important. Bad names can hide what a function does.
Yeah, that's frustrating. Like in that example, do rename, it doesn't really tell you what it does it?
Exactly. Do rename is vague. It's like, okay, what exactly does it rename?
Right. So how do you ensure you choose names that aren't vague?
Use explicit names. If you're renaming things in a certain way, reflect that in the name. Rename page and optionally all references shows the logic.
Wow, that's clear. But, aren't long names a bit, well, long?
It's a trade-off, and context matters. A long name is fine if it's called from one or two places. The extra clarity outweighs the length. If it's called in 20 places, we've got another thing to think about.
You mean maybe less long names in some cases?
Yeah. In Python, you might shorten it a bit. It's often more concise.
Ah, I see. So, a balance, right? Explicitness versus brevity.
Precisely. Look at code reviews, Andrew. Bad names are big red flags.
That makes sense. Thanks, Robert.
You bet. Clean code starts with clarity.
So, a well-named variable makes the code easier to follow, right?
Exactly. It's like having a good roadmap. If you know how to get to where you want to go on that road, you get to the destination faster and with fewer errors.
Makes sense. So you'd recommend specific names over generic ones, right?
Always.
Okay, Robert, so we were talking about naming conventions, and the previous chunk seemed to suggest some ways to enhance readability by using prefixes. But this chunk says to avoid encoding. Can you elaborate on why?
Yeah, absolutely. Avoiding encodings like more_f or vis_ is key for clean code. They're essentially redundant. Modern development environments usually provide the type and scope information elsewhere, in the code itself, or in metadata. It just clutters the names unnecessarily.
So, you're saying that these prefixes, often called Hungarian notation, are actually unnecessary baggage?
Exactly. They add to the noise, and make the code harder to read in the long run. Think of it like this. If you need to know the type, you'll already have the information in the actual code or you can look it up in the system, right?
Makes sense, but what if you have legacy code? Wouldn't avoiding these encodings lead to massive refactoring or make an existing system harder to maintain?
Well, that's a good point about legacy code. But in modern development, it's easier to adjust to new standards for the long term. And if you have a problem in the existing code, you need to address it.
So, you're suggesting a complete rewrite, or?
Not necessarily a complete rewrite, but a careful consideration of how those conventions could be replaced with more consistent and readable patterns. Just remember, clarity is essential. Less is often more, especially in code.
Okay, that's helpful. Any examples?
Sure. Imagine a variable named vis_image width versus just image width. The extra vis underscore prefix doesn't really tell you anything that you couldn't already derive from context.
I see. So, it's about the overall clarity and simplicity of the name itself.
Exactly. Keeping the names free of extraneous prefixes makes the code easier to understand and maintain.
Great insights. Thanks, Robert. Okay, Robert, so we've been talking about readability and writing clean code. But how do names themselves play such a huge role in this?
Names are absolutely critical. Think about it. If a function name is misleading, it's like having a cryptic instruction manual. You spend hours trying to figure out what it actually does.
I see. So, how do you avoid these cryptic names? Just be verbose?
Not always. You need a balance. Like in this test-ng example, getus is a bit of a problem. It only gives you half the picture.
Right? It sounds like it's only retrieving. What's missing?
It also creates the object if it hasn't been created. Thus, it's more than just getting an us.
So a better name would be more descriptive, like create or return us.
Exactly. That tells the whole story. You immediately know the function both retrieves and potentially creates. Think about the maintenance aspect.
Makes total sense. So it's not just about brevity. It's about clarity.
Absolutely. Clean code is self-documenting code, and descriptive names are a core part of that.
So, are there times where brevity actually might win out over complete descriptiveness?
Sure, in very specific, well-understood contexts. But for general-purpose code, good names are essential.
You make a compelling point. Thanks, Robert. You just clarified this key concept for me.
My pleasure.
Now, how about this? Should I maybe consider a trade-off between very descriptive names and code performance?
You know, that's a very good point. In some high-performance environments, you might need to optimize for speed. So a shorter name could sometimes be beneficial for speed, but the readability might be affected. We could explore more examples.
Great idea. Let's examine more cases.
Let's do that.
Hey, Robert, we've been chatting about writing clean code, and I'm thinking a lot about testing. It seems like a huge part of the equation. You know, how many tests do you really need in a test suite?
Yeah, Andrew, a common problem is that programmers think, that seems like enough. But it's fundamentally insufficient.
Insufficient? Why? What do you mean by everything that could possibly break? How can you ever truly know that you've thought of it all?
Well, think about it. You need to consider all possible inputs and edge cases. What if the input is outside the expected range? Or if something unexpected happens in the system you don't expect? A test needs to capture every condition that could cause the system to behave unexpectedly.
What about different types of tests? Unit tests, for instance?
Exactly. Unit tests isolate individual components. Then, you have integration tests to check interactions between different units. Good testing methodology requires combining different levels of testing.
That makes sense. So, it's not just about the number of tests, but the types of tests, right?
Exactly. You need a combination. And it's not always easy.
What are some practical strategies then?
Automation is key. It's way more efficient. You can run a wider range of tests and repeat them on each code change. That prevents regressions, which is really important.
So, let's say I'm building a calculator app. What sorts of tests would you need?
You'd need unit tests for individual operations: add, subtract, multiply, divide. You need integration tests to check how these operations interact. And then you need tests for edge cases, like division by zero or very large numbers.
So a good test strategy needs to consider diverse input and likely edge cases. It's not just that seems enough, right?
Right, Andrew. A lot of care and careful thought is necessary for thorough testing.
That's great. So, it sounds like a good test suite is more about strategic coverage of various cases than simply a numerical target.
Absolutely. That's the core principle, Andrew.
Thanks, Robert. Makes a lot more sense now.
You're welcome, Andrew.
So, Robert, you're saying that uncertainty in requirements can actually be part of the design?
Yeah, absolutely. It's unavoidable. Sometimes, the full picture isn't clear until you're digging in.
What's the best way to handle this ambiguity while coding?
Well, you can comment out tests that don't yet work because of that. Or use @ignore.
So, it's essentially like a placeholder for future work?
Precisely. But it's important to distinguish between a test failing because of unclear requirements and one that's simply not finished yet. Compile time errors require a different approach than runtime problems.
Why is that?
A compile time issue may have the most visible error message, and we can focus on fixing it at compile time. Ambiguity affecting runtime, we can document the potential issue to address it later.
Okay, so a detailed comment explaining the uncertainty is key?
Comments are good. Plus, it forces us to write the missing test.
Good point. So it's a sort of proactive risk management?
Exactly. We document it so that it's there when the requirement becomes clear later.
Great, and you can return to it as needed.
Yeah, it's a part of the iterative process. A good way to be upfront about possible issues.
Can you give me an example?
Sure. Imagine a function that calculates shipping costs. If the requirements are vague on handling international shipping, you can comment out the relevant parts of the test until the conditions are better defined.
That's clear. Helps us address the ambiguity.
Totally. Now, it's crucial to remember that these placeholders should be resolved, though. They're not a solution, they're a way of acknowledging the current uncertainty.
Makes perfect sense now. Good idea. Thanks, Robert. So, Robert, you mentioned testing boundary conditions. Can you break that down for me? What exactly are we talking about here?
Sure, Andrew. Boundary conditions, are those input values or states that lie at the very edge of an algorithm's defined range.
Okay, so like extreme values?
Exactly. Think of it like this. Imagine a function that calculates the area of a rectangle. You'd probably test input values where lengths are positive, but what about 0? Or negative? What about 0 dimensions? That's a boundary.
Gotcha. So, you're saying test the limits?
Yes, and not just the max and min values. It's crucial to test all edges of the input space.
So, this is about exhaustive testing?
Well, not always, you know. There's strategic thinking involved. Focus on those likely to cause errors. But a key idea, and a key mistake, is a common developer tendency to test just the midpoint.
Right, like the happy path, but missing the tricky bits?
Exactly. A well-known example is validating user input. Think of a form field. The boundary is that if the field is too long, or too short, or empty, it'll be a problem.
So, how do you practically figure out which ones these are? What tools or strategies?
Libraries like JUnit for Java or PyTest for Python make boundary testing relatively easy. You'd create test cases that specify input boundaries, expected outputs, and what to do if there is an error.
That makes perfect sense. A crucial part of clean code, then. Boundary conditions are key to robustness.
Absolutely. Well-tested code is code that works in all the cases we expect, not just the middle ground.
Great point, Rob. Thanks. This is really helpful.
Of course, Andrew. Any further questions?
Yeah, what are some good examples of boundary conditions in, say, image processing? I see this in lots of work I do.
In image processing, boundary conditions could refer to pixels near the edges of an image. If the image processing algorithm doesn't handle these pixels properly, you might get unexpected results, artifacts, or errors, and so on.
So, Robert, you're saying bugs tend to bunch up?
Yeah, exactly. Think of it like a domino effect. One bug can often trigger a cascade of others.
Well, I hadn't thought of it like that. So, how do we find them all?
That's where exhaustive testing comes in. You've got to thoroughly examine the function where you found the initial bug.
But exhaustive, how do we do that? Is that about every possible input?
Not necessarily every possible input, but a comprehensive set that covers all significant scenarios. You know, corner cases, edge cases.
Makes sense. Real-world example?
Imagine a payment processing system. If you find a bug where it fails to process certain amounts, you need to thoroughly test all payment types and amounts. Not just one type.
That makes sense. Sounds like mutation testing. Is that a tool?
Precisely. It tests by deliberately introducing changes to the code to see if the existing tests catch these mutations. It helps find those hidden dependencies.
So like making the code slightly wrong to see how it responds?
Exactly. It's a way to more deeply uncover vulnerabilities and flaws.
And what about large projects? How can you do this practically?
That's where careful planning and intelligent testing frameworks come in handy. You break down testing, prioritize tests that have the highest likelihood of uncovering further bugs.
So it's less about brute force and more about strategic force.
Exactly. And you can use static analysis tools too.
So, more than one technique, correct?
Yeah, a combination of techniques is often the most effective. You don't need to do them all on the first pass.
This is great. Testing is definitely more than just running tests.
It's about digging deeper, understanding the code's intricacies, and systematically finding faults that may appear to be isolated.
Thanks, Robert, for laying it all out so clearly.
You're welcome, Andrew. Now you're ready to do your own exhaustive testing and find those hidden bugs.
Hey, Robert, you've been talking about writing clean code, and now you're highlighting the importance of comprehensive tests. How do we know when a set of tests is truly complete?
Andrew, a complete test suite isn't just about having a lot of tests, but about having a well-structured set that's organized to uncover different failure modes. Think about it like a detective searching a crime scene.
So, a detective looking for clues. And what are these clues?
Patterns in failures. If you see a bunch of tests with inputs of a certain size failing, or tests involving negative numbers in specific arguments failing, you've got a strong hint about where the problem lies.
That's fascinating. But, wouldn't exhaustive testing take forever?
Totally. But what about smartly organized, strategic tests to find patterns? You don't need to test every single possibility, just focus on the cases more likely to uncover issues.
So, how do we organize tests to identify these patterns?
Consider what data your function will handle and structure tests that progressively test different parts or ranges of data. This will help uncover trends in the results, like sorting your tests by input size or data type.
So, if you see a pattern in failing tests, do you immediately know the root cause?
Not necessarily. The pattern points you to a likely region of the code to examine closely. Debugging still requires careful analysis.
Gotcha. So, patterns are a tool, not a solution, right?
Precisely. It's like a map that points to the terrain to explore.
Brilliant. A map to find bugs. So, are there any real-world examples?
Sure, if you're testing a function that calculates shipping costs, and you notice all orders over 1,000 units are failing, it probably means there's an overflow somewhere in your calculation.
Wow, that's incredibly helpful. Thanks, Robert. Rob, you talked a lot about clean code. But how does this relate to how fast our tests are?
Well, Andrew, clean code generally leads to more maintainable code. Faster tests often stem from good code design. What you don't want is a slow test suite that makes you skip tests when you have tight deadlines.
So you're saying fast tests are like a sign of clean code?
Absolutely. Clean code is often easier to reason about and has more predictable performance. That directly impacts test speed.
What are some strategies for writing tests that run quickly?
First, use the right tools. Modern frameworks optimize test execution and use caching strategies to avoid unnecessary repetition. Refactoring can help reduce overhead. A good example, if you have a lot of repeated actions in your tests, can you reuse them instead of running them multiple times?
That makes sense. But what about trade-offs?
Exactly, Andrew. You can't always sacrifice test coverage for speed, but you want a balance. You don't want to get caught up in optimizing tests too much that you miss important edge cases.
So we balance speed and comprehensive testing, right?
Precisely.
What if a test is inherently slow due to the nature of the operation being tested?
Pause. Then we might need to consider breaking down the complex test into smaller, quicker units.
Can you give me a real-world example?
Absolutely. In a banking application, a test checking large data transfer might take ages. Break this down into unit tests for data validation, data transfer, and data insertion. Each unit test takes a minimal amount of time but still tests the complete process.
So, break it down and optimize individual parts.
Yes, precisely.
Thanks, Rob. That makes a lot of sense.
You're welcome.